So let's take a look at Section 2, Potential Errors in Hypothesis Testing. So when you perform a hypothesis test, you have to make a decision. You are either going to reject the null hypothesis, or you are going to fail to reject the null hypothesis. Now remember that you are making a decision based on incomplete information. So you're inferring something from the information that you have. So you have to understand that you could be making the wrong decision. So there are two types of errors. One where you reject the null hypothesis but you really shouldn't have, and one where you fail to reject the null hypothesis but you really shouldn't have. Okay, so we call these errors type 1 errors and type 2 errors. So a type 1 error is the error of rejecting the null hypothesis when really the null hypothesis was true and you should not have rejected it. So we call the probability of a type 1 error of rejecting the null hypothesis when it was true, it's denoted by alpha, the Greek letter A, alpha. In a hypothesis test, the probability of a type 1 error alpha is also called the significance level. And then a type 2 error is actually just type 2 error is the error of failing to reject the null hypothesis when you really should have rejected it. So when it was false. Okay? So type 1 is rejecting H0 when you shouldn't have, and type 2 is not rejecting it when you really should have. And then the probability of that happening for a type 2 error is denoted by beta, and that's really found by 1 minus alpha. Okay, so let's take a look at this example. We have the U.S. Bureau of Transportation Statistics, and it reported that for 2008, 65.3% of all domestic passenger flights arrived on time, meaning that within 15 minutes of its scheduled arrival time. Okay? Suppose that an airline with a poor on-time record decides to offer its employees a bonus if the airline's proportion of on-time flights exceeds the overall industry rate of 0.653 in an upcoming month. So what would P be? Remember that our population statistic would be the actual proportion of the airline's flight time, or of the airline's flights that are on time. During whatever month of interest we're talking about, during the month of interest. Okay. So our hypothesis would be the null hypothesis is that that proportion is 0.653. The alternative hypothesis is that the proportion of flights would be greater than 0.653, right? Because they're going to give a bonus to those employees if they can get a higher percentage than 65.3%. Okay, so remember what a type 1 error is. A type 1 error is rejecting the null hypothesis when it was actually true. Okay. So in context of this problem, in this example, what would happen would we would say that the type 1 error would be concluding that the airline's on-time rate exceeds the overall industry rating when in fact the airline doesn't have a better record. So what would that mean to the people working on the airline? Well, if they concluded that, if they thought that the airline on-time rate exceeded the overall industry standard, what did they tell their employees? They told their employees that they would get a bonus, right? So they would give out a bonus to their employees, but they shouldn't be giving out that bonus because the employees didn't actually earn that bonus, right? And then a type 2 error in context of this problem. Remember what a type 2 error is. A type 2 error is failing to reject the null hypothesis when it is actually false. So what's happening is that the airline or the statistician would say, no, you did not exceed the overall industry rating. And so nobody gets a bonus, but in fact they really did exceed it. Right? So in context we would say that this is not concluding that the airline's on-time proportion is better than the industry standard when in fact it really is. So it is important to understand that in statistics you will make a decision and your decision could be wrong. Okay? There's no getting around that. Whenever we make decisions based on partial information, there's always that possibility. What you want to do is you have to weigh the risks of making that wrong decision. In the case of a type 1 error, the company's going to give out bonuses to people and pay them money when they didn't exceed that rate. In the type 2 error, the company is not going to give those employees any money, but the employees did step up and make that airline, beat the industry standard that was 65.3% of on-time flights. So let's look at one more example like this. Boston Scientific developed a new heart stent used to treat arteries blocked by heart disease. The new stent, called the Liberté, is made of thinner metal than heart stents currently in use, making it easier for doctors to direct the stent to a blockage. In order to obtain approval to sell the new Liberté stent, the Food and Drug Administration required Boston Scientific to provide evidence that the proportion of patients receiving the Liberté stent who experienced a reblocked artery was less than 0.1. Okay, so what we need to do is we need to first define our proportion, our population proportion, and we're talking about of patients receiving this Liberté stent, they experienced a reblocked artery, right? So we would say that this P is the proportion of patients receiving the Liberté stent who experience a blocked artery, who experience a reblocked artery. Okay. So our hypotheses would be that the null hypothesis is that that percent or of the population, or the proportion, would be 0.01. The alternative hypothesis would be that the proportion is less than 0.1, not 0.01, but 0.1. So, a type 1 error would be to conclude that the reblock proportion for the new stent is less than 0.1 when it really is greater, or is 0.1 or greater, right? So if that's a type 1, because remember, type 1 is that you reject the null hypothesis even though you shouldn't have. So what does that mean in context of this problem? Okay. It means that the FDA would approve this, right? The new stent is approved for sale, and then more patients will experience reblocked arteries. Okay. What would a type 2 error in this case mean? Remember that a type 2 error means that you rejected that you failed to reject a null hypothesis that is false, right? A type 2 error would be that you are not convinced that the reblock proportion for the new stent is less than 0.1 when it really is less than 0.1. So what would happen in the consequence of making this error in context of the problem? We could say that, you know, the new stent is not approved for sale. So doctors and patients, wrong kind of patients. Patients would not benefit from the new design. And so when you make a decision like this, which is the more dire of the two errors, a type 1 error or a type 2 error? Well, in this case, I would probably say that the more dire is a type 1 error, because a type 2 error means that you're not getting the new stent, which might make it easier for doctors to put in. And if the patients recover just as well as another one, a different kind of stent, then you're missing out on that. But the doctors have stents that they can put in to the patients, so it might make it a little bit easier for them to do it, but they're still capable of putting those stents in. So the type 1 error in this case, I think, is more problematic, because if they do approve this Liberté stent, it's approved for sale, doctors start using it because it is easier than the older ones, but then the patients have to come back in at a higher percent because they have reblocked arteries. Then there are a lot more consequences to that. So statisticians need to think carefully about a type 1 error and a type 2 error before they ever do any statistical analysis to decide which is the more important error to avoid. Sometimes the errors are, it's not going to affect things one way or the other, so it doesn't matter as much, but sometimes one error could kill somebody, and another error doesn't. And so you want to say, I need to reduce a particular type of error to the best of my ability when making decisions. Okay. So how about this? Let's look at alpha and beta. So the ideal test procedure would result in both alpha, the probability of a type 1 error, and beta, the probability of type 2 error, being 0. So alpha equals 0 and beta equals 0. Right? But this is really impossible to achieve. Since we have to base our decision on sample data, we're going to make an error one way or the other, right? So a standard test procedure allows us to select alpha as our significance level, but we really don't have any direct control over beta. Okay? So if we need to reduce alpha and try to make a type 1 error very, very small, then we make alpha very, very small. But what tends to happen is that beta is going to become bigger. And if we need to make the type 2 error very, very small, then we can make alpha actually bigger, and that will reduce beta. Okay, so let's consider this hypothesis. We have a null hypothesis that says P is 0.5. Our alternative hypothesis is that the proportion is greater than 0.5. So if this is the null hypothesis, that is the top end tail of the null hypothesis. And we're going to let alpha be 0.05. Okay, so this would represent this 0.05 for us right here. If the null hypothesis is false and the alternative hypothesis is true, remember the alternative hypothesis said that P was actually bigger than 0.5, we would have to pick this curve up, this one right here, and kind of move it, because 0.5 isn't it really wasn't our mean. Our mean would be somewhere up here bigger than 0.5. And so what we would see is the true proportion should, in this curve should be shifted to the right. And this tail right here would represent B. That is the probability of failing to reject a false null hypothesis, because if this is really, the alternative hypothesis is really true, there's a little bit of a probability right here that you would get in you could get a sample with this P being right in here, and that would be within our range of our null hypothesis, where we would think that the null hypothesis was true. Okay. If we look at this again, and say, what happens if, well, here we can do, this is the type 2 error. Okay. Now, if type 1, if our type or if our null hypothesis is true, there we go, then, and we got a value that's here, well, that is big enough and far enough away based on our alpha that we would reject the null hypothesis. But you know, there's a small chance that we just got that value and the null hypothesis is true. So this would be where our type 1 error comes from. Okay. We would reject the null hypothesis, but we really shouldn't have, because it was true to begin with. So now that was with an alpha of 0.05. If we make alpha a 0.01, so suppose here that we decrease alpha to 0.01. So we make alpha even smaller than it was. Well, that is decreasing our type 1 error. Our type 1 error, alpha, becomes very, very small. But remember, this line right here represents the fact that if the null hypothesis, if we should have rejected the null hypothesis and that alternative hypothesis was actually true, then what it does is it increases this type 2 error. Because there are more values now in that interval where we would fail to reject the null hypothesis when we really should have rejected it. So how do you decide what alpha level to use? Basically, you have to assess the consequences of the errors. Okay. Once you do that, you identify the largest alpha that is tolerable for the problem. And then what you do is you employ a test procedure that uses this maximum acceptable value rather than anything smaller as the level of significance. So what you're doing is you're saying this is what we can tolerate as far as being wrong. You decide whether or not the type 1 error or the type 2 error is the more dire, and then you make your decisions based on that. And what you have to remember is that by using a smaller alpha, that will increase beta. A smaller alpha increases beta. So when we look at this heart stents, and we kind of talked about this a little bit already, the consequence of making a type 1 error would be that the new stent is approved for sale and more patients would experience reblocked arteries. The consequence of making a type 2 error would be that the new stent is not approved for sale and patients and doctors wouldn't benefit from the design. So which one has the most serious consequence? We would say a type 1 error has a more serious consequence because it is a risk to patients' lives. Remember that, given that there are stents with lower reblock proportions available. So what should you do? Therefore, you should choose a small alpha. Okay. And so a small alpha might be something like 0.01 instead of 0.05. Something like that. If a type 2 error had been the more serious consequence, then you would want to choose a larger alpha, something like 0.05 or maybe even 0.1. Okay, but we always go through and think about the errors first, and they are a little bit confusing at first. You have to really think about your type 1 and your type 2 errors. Next, we'll be talking about the logic of hypothesis testing and then actually go through a procedure to do a hypothesis test.